purpose of today's lesson is for you to continue the progression of our timeline of the atomic model. So if you remember back, we started thousands of years ago talking about philosophers, Democritus and Aristotle, and we talked about why they did not have atomic theories because they had no experimental evidence. We talked about Dalton's model, the billiard ball model, and we talked about the gas experiments and the different laws that he used as evidence for those. We talked about Thomson's plum pudding model and the cathode ray tube, and we talked about the evidence of the cathode ray bending toward the positive plate, which is why he put these negative electrons within the model. We talked about the gold foil experiment done by Rutherford and how, based on Rutherford's result, he realized that the positive and negative matter can't be evenly distributed. Instead, the positive has to be in a really dense region that occasionally an alpha particle would bounce off of. From Rutherford's model, we went to Bohr, where we added these orbits, or energy levels, where the electrons had to stay. And we looked at the emission spectrum of a very simple atom, hydrogen, with one electron, in order to find evidence for that model. The last model we're going to be discussing this year is called the quantum mechanical, or electron cloud model. This model was created by mostly physicists, people like Schrödinger and Planck and Heisenberg, and it's actually very mathematical in nature. The problem with Bohr's model is that it really only worked with elements like hydrogen, things that have very, very low numbers of electrons. The emission spectrum, when you got more than, say, one electron in these orbits, became way too complicated to be described by simple circles. So instead, Schrödinger, Heisenberg, and Planck started working on a calculus-based quantum mechanical model. And in this model, we start thinking of the electron not as a particle, but more like a wave. Remember, Bohr was describing photons of light, which would be like particles of light. And he was saying that things like light, that we usually think of as waves, can also act like particles. So Schrödinger and Planck and Heisenberg, we're kind of turning that on its head. We're saying things like electrons that we classically think of as particles can also act with wave-like behavior. So picture an electron kind of traveling around a nucleus. But this time, instead of traveling on a circular orbit, we're going to have it travel as if it's a wave. So kind of up and down and up and down and up and down. There are certain distances from the nucleus where that path just continues on. That would be an allowable distance. But there's also some distances from the nucleus where once we get back to the beginning, it doesn't cross over nicely. That would be an unallowable distance. Based on this idea and the evidence from these more complex emission spectra, Schrödinger was able to come up with wave functions, which are actually calculus-based functions, to describe the motion of an electron as it's traveling around the nucleus, as an actual wave-like behavior. Now, these wave functions gave rise to a model of the atom where we don't have individual circles, but instead have these regions where electrons are most likely to be found. We call it a probability model because it's no longer trying to say the electron is here or the electron is here. Instead, it's describing the region and then saying the electron is somewhere within that region. So in order to really show this, let's start with a fairly simple element, something like oxygen. Oxygen on the periodic table is atomic number 8, which just means it has 8 protons in its nucleus. Now, if we're looking at a neutral atom of oxygen, that would mean it also would have to have 8 electrons in some sort of energy levels outside the nucleus to balance those protons. Based on the electron cloud or quantum mechanical model, the first 2 electrons in oxygen would be found in a fairly small spherical region, fairly close to the nucleus. Within that region, we would have one electron that's spinning on its own axis clockwise and one that's spinning counterclockwise. The second region would also be spherical, but it's going to be a little bit bigger. It's going to be further from the nucleus. And again, those spherical regions, they can each hold 2 electrons. So one would be spinning clockwise and one would be counterclockwise. The next 2 electrons are going to be found at the maximum of that same distance, but now instead of a sphere, we start getting more complex shapes. So the next two electrons would actually be found in a region that kind of looks like a figure 8 around the nucleus. But this figure 8 is three-dimensional, so it's kind of like an hourglass almost. Again, one's going to spin clockwise and one's going to be counterclockwise. And we're not saying that one is in the left lobe and one's in the right lobe. Those two electrons could be anywhere within that region. We're not exactly sure where. Remember, it's a probability model of describing the regions, not the exact location. So we said we had 2 in this blue circle, 2 in the red circle, 2 in this green region, and then the next one would actually be in that same size and shape region, but this time on the y-axis. And the very last electron would actually be same size, same region, shape, but now on the z-axis. So this is what the quantum mechanical model would look like for something like oxygen. It would have a nucleus in the middle. We would have a small circle, which you can kind of still see there, a bigger circle, and then 1, 2, 3 figure 8s. And that's just for 8 electrons. Now, you already see that this is kind of starting to look a little hazy. It's really difficult to distinguish the individual regions. And that's why the electron cloud or quantum mechanical model is generally not displayed as a pictorial representation like this. Just imagine trying to draw, instead of 1, 2, 3, 4, 5 regions, imagine just trying to draw like 18 regions. It becomes a hazy mess. You can't see anything. So there's actually a different way that we're going to be spending the next couple of days practicing, and it's called an orbital notation. And for oxygen, the orbital notation looks like this. And to a scientist, this orbital notation is actually giving the exact same information in a much clearer form than this model does. And that's our job for today, is really to try to describe how we can get the same information from the orbital notation as we did from the picture. So in order to figure this out, it's probably a little bit better if we build up our model and orbital notation at the same time. So I'm going to start by first drawing the first piece of the orbital notation, 1s, with the 2 arrows above it. And then I'm going to once again describe what oxygen actually looks like in its cloud. So we said the first region is a small sphere. We said there are 2 electrons in it, and that 1 electron spins clockwise and 1 of them spins counterclockwise. Now you might notice that in our orbital notation, we have a number. And the number in our orbital notation tells us the actual size of the region. So the number 1 is telling us that the region is small. A small region is going to be the region closest to the nucleus. You might also notice in our orbital notation that we have a letter. And the letter is what tells us the shape. So S was the shape that's our sphere. Now it'd be really nice if we actually always used the letter that was the first letter of the shape, but we don't. It really was just coincidence that S and sphere worked out for us. The next thing you might notice is that we have this line. And the line is going to give us some information about the orientation of our region around our X, Y, and Z axis. But you might notice that when I was talking about our sphere, I didn't say X, Y, or Z. And the reason that is because a sphere is really the same on the X, the Y, and the Z axis. There's no difference. It can be anywhere within those axes. So the line here, we only have one, because that orientation is simultaneously on all three. The last thing that I drew in then were these arrows, and you might have noticed that one arrow was facing up and one was facing down. The arrow direction is going to tell us the spin of the actual electron. And remember, the spin of the electron is actually describing what happens as it goes around its own axis. Not necessarily that it's going around the nucleus in one way or the other, but as it's traveling somewhere within that region, the electron itself is either spinning clockwise or counterclockwise as it goes around the region. But an electron can continue spinning or rotating around the nucleus in the same direction even if the spin is opposite. All right, so we've got 1s, meaning a small sphere. It's on all three of the axes. One arrow is up, one's down, so one's electron spinning clockwise and one is counterclockwise. The next thing I drew was a 2s, again with one line above it, and 2 arrows. Can you figure out the difference between the 1s and the 2s here based on our little key? If you remember, the second region that I drew was just a bigger sphere. So again, the 2 tells us the size. It was the second energy level out. The S tells us the shape. It's still a sphere. And there's one electron spinning clockwise and one spinning counterclockwise. After that, the next thing that I drew out was a 2p. And I put 3 lines above it this time. The first line had 2 arrows, one up, one down. And that line actually represents the x-axis, which is why the first figure 8 that I drew was along the x-axis. And we said there would be one electron spinning on its axis clockwise and one spinning counterclockwise as it moved somewhere within that region. The next line actually only got 1 arrow. That would represent the y-axis, which was the second figure 8 that I drew. And then finally, the third line also got 1 arrow, which would have represented the z-axis, which would be a figure 8 kind of coming off of the whiteboard at you, like that. So the number tells us the size. There was one that was a small size, and then there were 2 different shaped regions, spheres and figure 8s, that were the same size. So that's our blue sphere and our green figure 8s. The shape is determined by these letters. So S was sphere, P was figure 8s. The orientation around the X, Y, and Z axes was determined based on the lines. The S's only each got 1 line because they were on all the axes. The P got 3 lines because we could rotate that figure 8 on the X, the Y, and then the Z-axis. The arrows just simply represented the electrons and whether they were spinning clockwise or counterclockwise. These orbital notations can be written out for any element on the periodic table, but we're going to focus our attention on really just the first few rows on the periodic table to make our discussions a little bit easier. So if you think about the periodic table that I gave you on the first day of school, you may have noticed that there are several different shaped regions. It's not just one big block. And the reason that the periodic table is shaped the way it is because it's actually formed to give us information about the different regions within our diagrams. So the first thing that I'm going to do is I'm going to take helium, which is really over here, and just kind of move him over here with hydrogen so that we have one block like this. And then we've got the middle block, we've got the right-hand block, and then we've got these rows down here that are kind of all by themselves. I'm going to first remember the shape of each of these regions that are described on the periodic table using letters. So S, P, D, and F. You'll often see discussion about the S block or the D block. It really just means those parts of our periodic table. Once I know the identity of the parts of the periodic table, I can use the periodic table to actually figure out the order of these, what are called orbitals, that I draw in my electron configuration. And in order to do that, I have to not only letter, but also number the periodic table. So let me draw in my rows, which are also called periods on the periodic table. And then we'll really discuss how you can very easily number the periodic table. So over the next few days, you can practice drawing these orbital notations yourself. Okay, so we're going to number this, and when we number this, we're going to remember that these are the S's, these are the P's, these are the D's, and these are the F's. The S's are the first type that we're filling in our orbital notations. And because they're the first type, I'm going to start with the first one being a 1. So I'm just going to number this down: 1s, 2s, 3s, 4s, 5s, 6s, 7s. The P's are the second type. Remember, we had already seen that even in oxygen. But because they're the second type, I'm going to start with the number 2 when I number those. So that's 2p, 3p, 4p, 5p, 6p, 7p. The D's are the third type that we'll wind up using, so we'll start those with the number 3. That's 3D, 4D, 5D, 6D. And the F's are the fourth type we come to, so we'll go with 4F and 5F. Now for this class, we're probably never going to look at these F's because we're really going to focus on just the first few rows on the periodic table, but they are there, so it's kind of nice so that you can fill in the whole thing. Let's go back to oxygen, the one that we started with together. Oxygen is atomic number 8. So this is atomic number 1, 2, 3, 4, 5, 6, 7, 8. We're looking at an element right here. Now to get right here, we need to go through 1s, 2s, and 2p. And if you think back to our picture, our orbital notation, those are actually the 3 that we did go through: 1s, 2s, and 2p. The periodic table, as long as you look at the atomic numbers, will tell you what the next orbital to draw in is going to be. So let's practice really one of the longer ones you'll ever do. Let's practice this one right here. When we're doing these, we're going to need to remember, first of all, what each thing represents, but also how many lines to draw above each type of letter. There's a couple of ways you can remember it. And again, not that you're ever going to go with these down here in the F's, but I'll draw them out too. One way you can remember how many lines to draw is just based on the pattern. It goes 1, 3, 5, 7. The other way you can remember how many lines to draw is by looking at the number of elements that are in that type of region and then just dividing it in 2 because each line can hold 2. Either way is fine. Let's look at an example together, and then over the next few days you can really practice on your own. So let's start here with, let's look at potassium. Potassium is right here on the periodic table. It's the first element in this 4s region. No matter what element you start with, you're always going to start with atomic number 1 and 2. And atomic number 1 and 2, after you number your periodic table, you realize is at 1s. Element number 3 and 4 are underneath 1 and 2. So this is 2s. Element 5, 6, 7, 8, 9, and 10 are over here, which is 2p. Remember, p's always get 3 lines. Then we go to numbers 11 and 12, which is over here in 3s. 13, 14, 15, 16, 17, and 18 are all in 3p. And again, remember, p's always get 3 lines. And then finally, number 19 is where we said we were going to stop. That's in 4s. Now let's say that instead of stopping at number 19, we wanted to stop at number 20. Well, we would just have a second electron then in the 4s. Obviously, you're not going to be ready to draw these out on day one. We're going to practice together. We're going to keep looking at an example at the beginning of each period together. But I'm hoping that over the next 3 days, after you also have the flame test lab and some reading assignments done, you're really ready to start writing out at least the ones on the first 4 rows by yourself. The other thing we're going to be practicing as we go through this is identifying some vocabulary. You'll get to that in a little bit. And describing the region that an individual electron is in based on what is going to be known as our quantum numbers. So for instance, this electron that I just colored in red, I could look at this and say, oh, well, that's 4 rings away from the nucleus because the number tells us the size. It's in a sphere because the letter tells us the shape. It's going to be on all 3 of the axes because the orientation for a sphere shape is always on all 3. And it's going to be spinning clockwise on its own center because the arrow direction tells us the spin. Before the end of the week, it's really my hope that you are able to draw out some of our simpler orbital notations and describe what each of those things really represents in our electron cloud or quantum mechanical model. That's our goal, and that's what we'll be practicing.